Okay, before you start to do the calculations for energy balances and what I call the fun things of thermo, you have to know how to find properties. And first thing we're going to look at is properties of pure substances. In fact, for this whole course, we'll be focusing on pure substances. Till the very end, we'll get into a little bit about mixtures of water and air. But for now, we'll look at pure substances. And in this module, we're going to look at finding data from tables primarily. I'll give you a little bit about the nature of pure substances and talk about what we call saturated mixtures as well. Okay, the intensive properties of pure substances, and remember an extensive property is something like energy or volume that depends on mass. We can make that into an intensive property by dividing by the mass and calling it a specific property. So a specific property would be intensive, and so what I'll talk about now has to do with those properties as well. All intensive properties. An intensive property of pure substance is a function of two variables. Any two properties, call them Xi1 and Xi2, defines the state of a pure substance. Now those have to be independent pure properties. So two independent properties defines the state, meaning that if you have two properties, you can find the third. So the game is, for the next, I guess couple of weeks, you're going to be taking two properties and finding the third from those. And that's just a skill that you need to have and that you need to be proficient at to go forward and be able to solve energy balance problems, entropy balance problems, the things that we really want to get into later. Let me give you an example of how two properties define a substance. If you take an ideal gas, you know from chemistry that PV equals nRT. Now I've written nR sub UT here. I've written nR sub UT here, and R sub U represents the universal gas constant. Now some books, including yours, refer to the gas constant on a mass basis. So the R is just, they use the equation PV equals mRT. Now I like the one you learned in chemistry, PV equals nR sub U times T, where R sub U is the universal gas constant. The value that you'll have for metric units is typically 8.314 kilopascal meter cube per kilomole K, and so it's a molar basis, whereas sometimes in your book you may see in RT where the R has already been divided by the molecular weight. At any rate, I'm going to stick to this one so we only have one R to worry about, and that's the universal gas constant. In English units you'll have R is equal to 10.73 psi feet cubed per pound mole degree Rankine. So you want to have those things handy, and again, you always keep the units in your problem when you're solving problems, particularly when you're doing your homework. So PV equals N, and remember N is the mass over the molecular weight times R times T. Now the specific volume is the volume per mass, and that's an intensive property, is equal to RUT over P molecular weight. R is equal to RT over P, where the R without the U has already been divided by the molecular weight. Important thing to recognize here is that once you've determined what gas it is, say water or oxygen, then the only things that you only need two properties to define the volume. So notice V equals RT over P, R, T and P will give you V, or inversely you could say if I knew P and V, I could find T. Now I want to talk about the nature of pure substances and how they all behave. If you take a pot and put it on the stove, then you heat it up, what you'll find is that the temperature starts to increase as you add heat. Now that you have the liquid. If you start from a liquid, you put water in there, say at 30 degrees C, you go and you'll heat it up until it reaches its boiling point. The volume will increase as you do that. You have the volume expanding with temperature till you reach 100 degrees. Once you reach 100 degrees, the temperature will quit changing and it'll start to boil. As it starts to boil, the volume will increase quite a lot, quite largely. You'll have a huge increase in volume here. I don't think this picture does it justice, but as the liquid becomes vapor, you have especially for low pressures, you have a very large increase in volume. That point is called saturation. Once it's all boiled, the gas expands further, and you have a further increase of temperature. But while it's boiling, if the pressure is fixed, then the temperature will stay constant. And here we fixed the pressure at 1 atmosphere, which is about 1.01 bar, or about 101 kilopascals. The temperature, what we call the saturation temperature, and you know that is the boiling point, will stay at 100 degrees as long as the pressure remains 1 atmosphere. So between points 2 and 3, you have what's called a saturated mixture, where it's going from all liquid to all gas. We define these points as VF and VG. So if you look in your steam tables, and don't worry if you don't get exactly this number, because depending on the book, the steam table, the values in the steam tables will be just slightly different, but you should find something close to VF is about 0.001043 meters cubed per kilogram, and VG, much, much larger, the gas, 1.672 meters cubed per kilogram. So between boiled and between just about to boil and just boiled, we call that saturated. And in there we say we have a saturated mixture. Now, saturated liquid is the one that's just about to vaporize, and the values you'll see in your tables will be VF, UF, HF, and SF for volume, internal energy, enthalpy, and entropy. Saturated vapor, just vaporized, will have VG, UG, HG, and SG. Volume, internal energy, enthalpy, and entropy. And those are properties that we're going to use when we do calculations on processes later on. Now what if I put it in a pressure cooker? What if I raise the pressure? Now this can happen either in your kitchen or in your radiator. The water in your radiator, if you only had water in there, then you'll try and keep it from boiling at 100 degrees C. And so what you'll do is you'll put a cap on there that'll force the pressure. It won't let water out, won't let water escape from your radiator until it gets to a higher pressure. And typically a radiator will add 1 atmosphere to the pressure. So in this case, or in a pressure cooker, you could add up to about 1 atmosphere. If you do that, then you'll raise the boiling point. So the boiling point, or what we call the saturation temperature, depends on the pressure. So the higher the pressure, the higher the boiling point. Now this is interesting. If you go up in the mountains, then the pressure will drop, the atmospheric pressure will drop. And so if you go to cook something in the mountains, it'll take much longer because you'll be boiling it, but you'll be down at a lower than 1 atmosphere, so you'll be lower than 212 Fahrenheit, or lower than 100 degrees C when you're boiling it. And cooking is a function of temperature. Cooking is actually a chemical reaction that depends on temperature and slows way down when you lower the temperature. So I've had that experience personally, and it's cost us extra time to wait to eat dinner, particularly things that take a long time to cook, like beans, for instance. Raising pressure raises the boiling point temperature, what we call the saturation temperature. So that's something you really want to have a good feel for. Now we look at the saturation curve, where you have this saturation pressure versus temperature, and notice that any point on this curve will be the saturation temperature for that pressure or vice versa. Along the line, anywhere along that line, this blue line, you'll have a mixture, or just liquid, or just about to be all vapor. Somewhere in between saturated liquid and saturated vapor, you're on that line. If you raise the pressure of something that's on that line, it will bring you down into, or when you raise the pressure, it will bring you up into the liquid region. And we often call that a compressed liquid. If I lower the pressure, it'll put me into the vapor region. So the other way of looking at that is if you're on the line and you raise the temperature, then it'll go into the, at a fixed pressure. Say I'm boiling at 100 degrees, and I've just boiled it all and I want to raise the temperature, then that'll put me into the vapor region. I'll be going to the right from that curve. And we call that a superheated vapor. Another way of looking at it is if I'm sitting on the line and I lower the temperature, then it will first become liquid, and if I try to lower the temperature at a given pressure below the saturation. Now, one thing we want to keep in mind is that if we are in a saturated state, then the temperature is a function of pressure, or the pressure is a function of temperature. In your saturated tables, you can find, for any given temperature, you can find a saturation pressure. And for any given pressure, you can find a saturation temperature. That's as long as you're below the critical point, but we'll get to that later. So we call these dependent properties. T and P are dependent on each other at saturation, so you can't use them as, in other words, if I know T and P and it happens to be the saturation temperature for a given pressure, then that really only counts as one property when you're trying to find other properties. In that case, we need an additional property. So say I'm saturated and I want to know the energy or the volume or something like that. Then what you need is, well, how much is liquid and how much is vapor? So to describe a saturated mixture, we need to know how much is vapor, and we call that the quality. So the quality is the mass of vapor divided by the mass of the mixture. And on this little diagram I've indicated as a fraction how far between the saturated liquid value, VF, and the saturated vapor value, you are on a mass basis. So X would be the fraction of vapor. 1 minus X would be the fraction of liquid. So when we want to find a mixture property, we'll take that to be the volume of the mixture is the fraction of the mixture times the specific volume of the liquid. 1 minus X, the fraction of the liquid, times the specific volume of the liquid, plus X, the fraction of vapor, times the specific volume of the vapor. And again, that's the mass fraction, as you see on the second equation here. Mass of the liquid over mass of the mixture. That's the mass fraction of liquid, 1 minus X. Mass of the vapor over the mass of the mixture is X, and that's the mass fraction of vapor, or what we call the quality. So that's the total liquid volume plus the total vapor volume is the total volume divided by the mixture mass, which if we take that to be 1 pound mass or 1 kilogram, then what we'll get is the specific volume of the mixture. Let's take an example. And if you follow along with your book, maybe pause the recording, take out your book, and go to the saturated tables find your metric tables. You'll have sets of metric tables and English unit tables. Go to the metric unit tables, and we're going to try to find the volume of 100 degrees seawater at 70% quality. So take out your book and go to the tables. Don't worry if your numbers don't exactly match this, because again, every book will have slightly different values in the steam tables depending on how they calculated them. Should be all the same, but in fact it's not. So the volume of the liquid equals 0.0010435. Now that's at 100 degrees C. Find that point. Volume of the liquid, VF, 0.0010435. Now for our example, where it's 30% liquid, I'll take 1 minus 0.7, or 0.3, times VF, and I'll get the volume taken up by the liquid in that mixture. Comes out to 0.00031 meters cubed. Do the same thing for the volume of the gas, and that's 1.673 meters cubed per kilogram is what you should find, or something close to that. Then 0.7, it's the 70% vapor, times that volume comes to 1.1711. You see that on a volume basis, you've got almost all vapor there. On a mass basis, you've got 30% liquid. But the liquid takes up such a smaller space that on a volume basis, it's like 99 plus percent vapor. So a very big difference between a volume fraction and a mass fraction. We track things with mass fractions, the quality. So solving that, 1 minus xVF plus xVg equals 1.174. And again, that's meters cubed per kilogram. And again, notice that a percent vapor on a volume basis for this problem, 99.97%. Because, of course, especially at low pressures, the vapor takes up so much more space than the liquid. Much greater percentage than the 70% vapor that we found from the quality, which is a mass fraction. Quality is a mass fraction. Again, we're going to track things: volume, enthalpy, internal energy. All of those things we're going to track with a mass fraction quality. Although sometimes you need to know what the volume fraction is. So again, we can do that with calculations. Again, other specific properties follow the same general pattern. Volume, internal energy, enthalpy, and entropy. Those are the primary ones we're looking at in your introductory thermodynamics course. Now I want to talk about a thing called the critical state. The critical state is the point where you've just gotten to where you can no longer turn a vapor into a liquid. So we call this above the critical temperature and pressure. We call it a supercritical fluid, but it behaves like a very dense gas. So if I take, now you notice that the specific volume of the liquid keeps getting larger. This really isn't to scale, but as you go up in pressure, the specific volume of the liquid gets a little larger because, of course, the temperature is rising too. The saturation temperature is rising. So VF will go up with pressure going up and temperature going up. But VG gets smaller. And what happens is eventually they get to where there's no difference between them. We call that the critical point. The critical temperature is the temperature above which you cannot condense a gas. So if you take something like air is made up of mostly nitrogen. So let's suppose we took pure nitrogen gas and we tried to condense it. Well, you wouldn't be able to at room temperature because the critical temperature for nitrogen is minus 100 and something degrees Celsius. It's very cold. So you just won't be able to. You won't be able to condense it. You've got to get it very cold to condense the nitrogen gas. So let me give you an example of some of these critical point properties. What I recommend you do is go to the back of your book or somewhere on the internet, let's say, and find and find the critical properties, critical temperatures of some various things. Like, for instance, the critical temperature of water vapor, or of water, is 647 degrees Kelvin. That's pretty hot. That turns out to be about 705 degrees Fahrenheit. Very hot. But if you take something like, and so you commonly see water, liquid, at room temperature. If you take something, on the other hand, like, I said nitrogen, its critical temperature is 126 degrees Kelvin. That's about minus 150 degrees centigrade. And so you've got to get it very, very cold to get liquid nitrogen. If you take something like methane, methane is the main ingredient in natural gas. And methane has a critical temperature of 191 degrees Kelvin, which is, oh gosh, that's minus 80 or so degrees centigrade. Very, very cold. But we often have to make liquid methane. In fact, in our region, we have a lot of LNG, liquefied natural gas plants, and they're contained in huge tanks. Those tanks have to be extremely well insulated because the liquid inside of those tanks is very, very cold, and you don't want a lot of heat getting in there and vaporizing all that gas. So that's to store something very cold, you have to have a lot of insulation to keep it very cold. And again, the critical point is the temperature. Let's put it this way: if you're above the critical point, you cannot have a liquid. Okay, now let's look at what we call a subcooled liquid. A subcooled liquid is a liquid that's cooled below its saturation temperature for a given pressure. So, for instance, if you're boiling water at 14.7 psi, 212 degrees Fahrenheit, or let's say 1 atmosphere, 100 degrees C, boiling point of water, normal boiling point of water at 1 atmosphere, and I cool it down to, say, 90 degrees C, it's definitely going to be a liquid. Let's say in the equilibrium state, it'll be a liquid. So we just think of that as a regular liquid, but it's often called a subcooled liquid because it's below its saturation temperature for a given pressure. We also call that a compressed liquid because, by the same token, if I had water boiling at 100 degrees C and then I raise the pressure onto that water, then it's going to stop boiling. It would need to get up to, say, 120 degrees C before it start boiling again. If I double the pressure, say, to 2 atmospheres, then it would need to raise up. So we call that a compressed liquid because I've raised the pressure above its saturation pressure for that temperature. Again, it will be a liquid. You could have those two names mean pretty much that you have a liquid that's not saturated. So our common experience of a liquid water is a compressed or a subcooled liquid when it comes out of the faucet at room temperature. Now, superheated vapor is one that's heated above its saturation temperature for a given pressure. So that's what we normally think of as just a vapor. Once it's boiled, it becomes a vapor, and then if I raise the temperature above the saturation temperature, then it becomes a superheated vapor. So if it's still at its saturation temperature and it's all vapor, I call that a saturated vapor. If it's above its saturation temperature, call that a superheated vapor. So what we've looked at is the properties of pure substances. Learn that given two properties, you can find a third. And I recommend you go and just start doing that. Practice that, because you never know which two properties you're going to have, and you want to have that as a skill that you can just do quickly. These two properties must be independent, so if you have saturation and you have the saturation temperature and saturation pressure, that doesn't tell you enough. You have to know, well, let's say, how much is liquid and how much is vapor, and we do that with a property we call the quality. Again, saturated mixtures, recapping again, saturated mixtures, the saturation temperature is a function of the saturation pressure, and the properties then will be a function of the quality once you know that it's saturated and you know either the temperature or the pressure. So we'll use the quality of the mass fraction to find the volume or the entropy or the enthalpy. So on your homework, I want you to go to Blackboard, and there'll be a problem set there, and just work as many of those problems as you can.